So we saw earlier what happens when you put a negative to an equation, whether it's a negative that's inside or a negative that's outside. But you're also going to notice that um, it's going to have a lot of similarities with the up, down, left, and right movements. If we see a negative, like you see here, inside with the x, that is going to directly affect the x values. That is going to be a horizontal, but this time a negative is going to reflect. Let's make that yellow. If we need a second color, I like purple. Not a Vikings fan, I just yellow and purple. I like purple, especially for highlighters. So reflections in the coordinate axis happen when we put a negative somewhere in our function that's either going to affect the x or the y value. A reflection over the x value is going to, or over the x-axis, goes in front of the function. That is, you made the function itself negative. That is a vertical reflection. A reflection in the y-axis, that is going to go from left to right, or right to left, depending, happens inside the function. A reflection over the y-axis is a horizontal reflection. That is affecting the x value. So what used to be a positive x becomes a negative x. For vertical, what used to be a positive y becomes a negative y. So it is reflecting over the x-axis but affects the y values. For the reflection over the y-axis, the horizontal reflection, it changes the x values because now the x's become opposite as opposed to the y's becoming opposite. Take a look at both of these examples. This equation, the absolute value of x plus 3, has been moved. And as we know, plus 3 on the inside moves the original absolute value. And if you're curious as to what it looks like for an absolute value equation, here's the parent function. This is absolute value of x. We don't need this one, but why not have it as well? This is the parent function, and as we notice, the parent has moved plus 3. That is left 3 spots. It happens on the inside, it moves to the left. 1, 2, 3. There's that point. 1, 2, 3. There's that one. This one, 1, 2, 3. So in each case, those points moved. This one represents a left shift of 3 units because it says plus 3 in the equation. Now for this one is the same thing. It did move 3 units to the left, but then it also reflects because of the negative, reflects over the y-axis. So now what used to be a negative or a positive 3 or a negative 3 for the x, for example here, I move over 3 spots, 1, 2, 3 is at negative 3. But then I have to make the x the opposite, so negative 3 becomes positive 3. Same thing here. If I was to take this point that is at negative 2, 1, the x is negative, now becomes positive 2, 1. Now keep in mind, this point right here connects to this point right here. And then for this last one, what is at 4, or negative 4, positive 1, is now going to be positive 4, positive 1. The x values have become opposite. It's reflecting over the y-axis. So these two points here are the same. These 2 points here are the same. And then these 2 points here are the same. So just be mindful of which ones are the representative reflections over the y-axis. The furthest away would be matched up with the furthest away. But it is a vertical, or this time it's a horizontal reflection because it's directly affecting the x value. It's inside the function. So it's going to flip it over the y-axis. It's weird to think about because it's a horizontal reflection. Horizontal, it's the x-axis that we count horizontally, but we're reflecting over the y-axis. Let's take a look at another kind. What kind of reflection do we have this time? And how do we know, first of all, it's a reflection, other than the big word reflection at the top of the board? Well, it's got a negative. The negative is in front of x squared. Therefore, this time it's not going to be a horizontal reflection, but rather it's going to be a vertical reflection. It is going to shift over the x-axis. It is a vertical reflection. And this affects the y values. Now remember, f of x is the same thing as y equals. So when you say, I'm going to make f of x negative, you're literally making the y values negative. So there's our good old x squared. Here's our parent function, our quadratic. Along with it, we're going to graph negative x squared. So if you want to try to plot both of those on the same graph, go ahead and pause for a second. Try that out. And then compare that with the answer that I'm going to give you right now. So there it is. There's the parent function. F of x equals x squared. 0, 0, 1, 1. Keep going. Negative 1, positive 1. There's the parent function. This time I'm going to take each one of those points and flip it over the x-axis, meaning I'm going to make the y values negative. So 0, negative is still 0. Call it negative 0 if you want. Doesn't matter. Negative 1, positive 1 becomes negative 1, negative 1. So the y values are now opposite. And then instead of positive 1 for the y, it becomes negative 1 for the y. And so notice how those match by simply flipping the points over. And so this one should also be red. But is your art lesson for today? When I mix the red and the blue, I should actually get purple. So we see a vertical reflection this time. Affects the y value. It's flipping over the x-axis. A lot of variables kind of flying around there. Just to make sure you understand. Negative on the outside is going to flip it vertically. Alright, so here's your time to shine. I am giving you right now a parent function. The parent function happens to be x to the 4th power. I haven't talked about this one. If you want to know the appropriate name for it, it's a quartic function. It is to the 4th power. It is the parent function. It goes through 0, 0. It goes through 1, 1, just like squaring does. But when I get to 2 to the 4th power, that's 2 times 2 times 2 times 2. That's 16. This thing is going to go up a lot faster than the quadratic did. Also, for that same reason, when I start getting into fractions, and I say 1 and then over 2, and then take that to the 4th power, it becomes 1 over 16. So you notice the difference between a quartic and a quadratic. It's a lot flatter in the middle portion where the fractions would happen between negative 1 and positive 1. It just flattens out a lot more. But it looks a lot like our quadratic equation did. So your task is to write the equations having seen the transformations that took place. So if you would like to pause real quick and give those a shot, go ahead and do so. If not, let's talk about what's happening here. On this first one, this thing looks like it moved up 2 spots, but then it also flipped upside down. So it's reflected vertically and moved up 2 spots. So a vertical reflection, first of all, the moving up 2 spots will do that. That's easy. That's just plus 2 on the outside. The fact that it flipped vertically means that I have to take the original and put a negative in front of it. So this becomes negative x to the 4th plus 2. So hopefully you got that right. If not, just again check to make sure that 1, you've moved this up 2 spots and then it's also reflected. With that in mind, that kind of helps us with this next one a little bit. It's reflected. It's also moved this time to the right. So again, if you want to give this a shot, pause, write the equation, and let's see if you got it right. It moved to the right 3 spots. So in the equation, because it's moving left and right, it needs to look opposite. So to the right 3 spots on the equation looks like a minus 3. And it is before you apply the 4th power. Then because it's reflected, we put a negative in front of the function itself. And so outside the parentheses, we get a negative, and then x minus 3 to the 4th power. Keep in mind, when it comes to square root functions, functions that have a restricted domain, any transformations that take place, that has to go along with it. So the domain of the original square root function, the square root of x, if I make that negative, I've reflected that vertically, I'm not affecting the x values. Now remember that everything inside the parenthesis, or inside the square root, everything inside for the top one, x, which is the inside portion, has to be greater than or equal to 0. Okay? That's why you see that up there. X is greater than or equal to 0. Then, look at the next one though. We're going to make this one red. The next one reads negative x. This has to be greater than or equal to 0 as well, because it is, in fact, a square root. But we can't leave that as negative x. We have to solve for it. So we divide by negative 1. And so 0 divided by negative 1 is negative 0. I just like saying that. And then remember that when we divide by a negative with an inequality, we have to flip the sign. That's why you see that as less than or equal to 0. Because if you use positive numbers now, it's not going to play nice. But if you use negative values, a negative becomes negative. Negative makes positive. Okay, now it's not going to break the square root. And then last one, let's make it green. This one reads x plus 2. And this has to be greater than or equal to 0 because it's inside the square root. So when I solve that, I subtract 2 from both sides. X is greater than or equal to negative 2. And that's why you see the domain now. The only thing I can do is make sure I use values that are greater than or equal to negative 2. That keeps everything inside the square root positive. With that in mind, again, if you just graph the original, you can apply transformations to it. But let's try that out. Let's graph these using only transformations. Now, number 4 we haven't talked about. So we're going to wait on number 4. But just in case you want to try that, we're going to go ahead and add that to the graph as well. We're going to save that one for last, though. So if you want to go ahead and try these out, go ahead and pause and graph them. If not, then take a look. We start off again with the parent function, the square root. What does that guy look like? So 1, 2, 3, 4, 5, 6, 7, 8, 9. A little over the top, but I'll do it anyway. 4, 5, 6, 7, 8, 9. I like to be extra sometimes. Don't need that many on the y value, probably. Now I'm just getting lazy. So the original function, square root of x, looks like the rocket. Remember that one? Starts at 0, 0. Remember, it has to be greater than or equal to 0 in order for it to work. It is a restricted domain. Then the next number I can take the square root of is 1. So 1, take the square root is 1. Then the next number is 4. Square root of 4 is 2. Square root of 9 is 3. And again, I probably didn't need to go all the way there, but I wanted to just to get a better look at this graph. So here's my parent function. Looks like a rocket, just taking off from the ground, going straight across. So it's going to change in x values a lot faster. It's going to change in y values. So here's our original. What's happening with number 2? Let's talk transformations first. A negative in front is going to reflect and it's going to be a vertical reflection. That is, the y values become negative. It's happening after the square root has taken part. So it's affecting the function values, that is the y values. So 0 becomes negative 0. 1, 1 becomes 1, negative 1. 2, 4, or 4, 2 becomes 4, negative 2. And then 9, 3 becomes 9, negative 3. So it just looks like it's upside down. And now it looks like a sideways parabola. For that matter, remember, if we take the square root of a function, or the square root of anything, we look at plus or minus, we just created plus or minus the square root of x. Now, let's look at number 3. Number 3, the negative is inside the function. Inside happens to the x. This is a reflection because of the negative, but this time it's horizontal. So that means the x values now have to become opposite. So 0, opposite of 0 is still 0. Positive 1, 1 becomes negative 1, 1. Positive 4, 2 becomes negative 4, 2. The x values are becoming opposite, or negative in this case. 9, 3 becomes negative 9, 3. Now I'm running into my words, so I'm going to make this one stop short after that with an arrow. So there we go. Now we've graphed the red one, a reflection of the parent function, but a horizontal reflection. Let's go green. Always good. Keep your eco footprint small. X minus 3. This thing is going to be moving left or right? Right 3. Then negative on the outside, not in front of x. So don't let that negative minus 3 fool you. That minus 3 is a left and right movement. There's not a negative in front of x, so that's not changing the x values. But there's a negative in front of the square root, which is going to reflect. It's going to change my function values, and it's going to be a vertical. Let me put vert reflect. So to the right 3, so here's the original. Now it's already covered by the other colors. So now, well, that's still the starting point for the parent function. We're not going to forget that. Right 3 spots, 1, 2, 3, and it does nothing else, so 0 becomes negative 0. Well, still 0. Then the next point is going to be at 1, 1. I'm going to move to the right 3 spots, 1, 2, 3, and it's going to reflect vertically, so positive 1 becomes negative 1. Likewise, this next one is at 4, 2, so I'm going to go to the right 3, 1, 2, 3, and 4, 2 becomes 4, negative 2. Well, 7 now because I moved it to the right 3 spots. And then I connect those. I'm not going to do the 9 just because it's off my chart. I don't want to. And that last line got a little sloppy. That's going to bother me, so I'm going to redo it. Let's see if that's better. That's good. So there we go. We move to the right 3. We reflect it vertically. And that becomes our graph for number 5. Now for the last one, as I promised you, we haven't really talked about this yet. But let's see if we can kind of piece this one together. For number 4, it looks like it's happening to the outside. So if I take the square root of x, I'm going to multiply that by 2. So that means square root of 0 is 0 times 2 is still 0. Square root of 1 is 1 times 2 is now 2. Square root of 4, right here, square root of 4 is 2 times 2 is 4. And square root of 9 is 3. 3 times 2 is 6. Missed. 1, 2, 3, 4, 5, 6 right here. So what happened when I put a 2 in front of the function? Compare the purple and the black line. What happened? We're going to talk about it in just a second.